Hello, welcome to Apply Database 1. In this session, we will address redesigning databases. To do that, we need to examine the original database design through queries that will explore the internal caves of the database. In previous sessions, we identified entities, their attributes, and their relationships to create a model, then created a database design, and translated that design into SQL code to create the database itself. When redesigning the database, we explore the code, translate that code into a database design, then identify the entities and their attributes and the relationship. So if we need to eliminate, add, adjust, or update any of the information at that point, then we can do that. The process of going backward to understand the database design is called reverse engineering. When the database is old, not efficient, includes errors, or not compatible with new systems, there is a need to redesign the existing data to fix these problems and increase efficiency. To adapt to system requirements changes, we need to redesign the database. Installing a new information system will also require the redesign of the existing database, not only to work with the new system, but also to work with users' behaviors. One of the ways to query and explore an existing database is correlated subquery, which looks similar to a subquery, but processing it will be different. In the correlated subquery, the processing is nested. That is, a row from the upper query statement is used in comparison with rows in a lower level query, while in the regular subquery, the processing from the bottom up. This slide shows the subquery that we used in a previous session in the example of the Viewridge Gallery small business. This subquery contains two separate tables in the levels of the query. The artist in the top level query while work in the subquery as shown in the code. But what if we decided to use title to be alternate key? What if there was similar titles? For example, that mystic fabric is repeated somewhere. To solve such a problem, we use the correlated subquery where it contains the same tables in both levels of the query. The subquery purpose is to check if we have in the table title two work IDs with the same title. Once I know that that there is a duplicate, then I can either change the title or not use title as my alternative key. Also, correlated subquery can be used to check for any rows that violates the functional dependency. For example, if we would like to check that no two or departments have the same budget code, then we use the nested correlated subquery that's shown here. Other specialized forms of correlated subqueries are exist and not exist. An exist condition is true if any row in the subquery meets the specified conditions. A not exist condition is true only if all rows in the subquery do not meet that specified condition. We can also use double not exists to find rows that have some specified condition to every row of a table. If we go back to the example of functional dependencies, we can use exist subquery to check that no two departments have the same budget code as shown in the SQL code here. And you can see that we used exists to check for the department and budget code. As an example of double not exist, let's assume that we want to know the name of any artist that every customer is interested in. To do that, we can find all customers who are interested in a certain artist, then take the complement. If the complement is empty, then all customers are interested. The first not exist was to select the customer ID from the customer table, and the second not exist is to match that with the artist using the customer artist interest table. We looked at the database and we found that there is a need to redesign it. Let's assume that we would like to change the primary key. Can we do that? What will happen if we do so? What might be affected if we change the primary key? What if something failed during the change? When redesigning database, there are three things that you have to consider. First, you need to understand the current structure and contents of the database before making any structure changes. Second, test the new changes on a test database before making real changes. Do not make the changes on the operational database. Actually, that will lead us to the third, which is you have to have a backup, complete backup of the operational database before making any structural changes. Do not use the changes on the operational database. One of the techniques that we use to understand the database is reverse engineering. So, and this is what we talked about in the first slide, actually. Uh, so, uh, we develop usually we develop the model, then translated that into design. In the reverse engineering, in this situation we will reverse the process, which means we already have an existing code that will be converted into a design that will be used into a model, and then we can identify entities, their attributes, and their relationships. This process is the one that's called reverse engineering, as we stated before. This will be used to provide the basis to begin the database redesign. The best about this model that it's not conceptual, but it's not also an internal schema. It has the characteristics of both. Once we create the model, we study it very well to understand the nature of the database that we are dealing with. During that, we should be careful since it, in most cases, it will be missing some information. And again, we stated that before, that one of the problems that you will see in a database is missing data. This is a reverse engineered data model which shows the initial relationships between the entities, but without identifying maximum or minimum cardinality. We just put arrows here. We understand that we have customer, artist, work, transaction, and then we created an intersection between the customer and the artist. And that was just an initial thought. And as you can see, the arrows doesn't have any information. It doesn't say if it is one to many, many to one, or many to many, or it doesn't say that it's optional, mandatory relationship. Then with understanding the database, we start adding more information as we get the information, and analyzing that, understanding what we have. And then we will have the primary keys, the foreign keys, the data type, the null not null concerns, and other information. From that, we can develop the one to many, optional to mandatory relationships, and add it to the database design. So now I have the database design. So I have the schema, the database design, and I will try from this to go back to the entities and see if I need to change some of these columns, delete some of these columns, maybe extra information that I don't need or I don't use anymore. How can I make this data work with the new system that we got, or fix the errors, the mistakes that we have in the previous database. Another tool that we can use when redesigning or trying to understand a database is a dependency graph. Dependency graph are diagrams used to portray the dependency of one element on another. Dependency graphs are not graphical displays like bar chart or histograms. They are diagrams that consist of nodes and arches or arcs, um, or lines that connects these nodes. This is a reverse engineering dependency graph that shows the table customer with two views. If a change happens, the dependency graph will provide an idea on what other parts of the database will be affected. For example, tables, triggers, stored procedures, relationships, so on. This dependency graph shows another example of reverse engineering results. It is considered a good starting point, although it's not quite correct. You can see that the database design, um, or the graph, the dependency graph, was not able to interpret the join that creates the artist work net view. This view, it was not uh, interpreted or translated in a good way, so we don't know what this means. This is a partial dependency graph that was drawn using the results of the entity relationship model. Some of the views, stored procedures, and constraints are not shown just for simplicity. Although it's partial, it shows the complexity of the dependencies among database structures. Uh, can you imagine what might happen if you do a change in the transaction table? If we do any changes in this one, what would that affect from the entities or the tables around that, or views or triggers? Once we identify the errors, mistakes, or other issues in the database, we can make changes. But before making any changes to an operational database, remember, we need to create a complete backup of the operational database. Then an offline testing database should be used to thoroughly test the changes. It's recommended to have three different copies of the database schema during the redesign process. We will have like a small test database for initial testing, a large test database for secondary testing, and then the operational database that will stay live operational on the side, uh, and we will never touch the operational data while testing. Once the implementation is successful, at that point we can phase in, phase out between the new database and the previous operational database. Some of the database redesign changes are changes or changing tables and columns, such as changing table names, adding and dropping table columns, changing data type or constraints, adding and dropping constraints. We can also change relationships, such as changing cardinalities, maximum, minimum. We can change the one to many into many to many, or the other way around. Adding and deleting relationships, adding and removing relationship for denormalization purposes. There is no SQL code or SQL code or command to change table name. Unfortunately, the table needs to be recreated under the new name, tested, and the old table should be dropped. The data can be copied from the old table to the new table, of course, before you drop the old one. But changing a table name has a number of potential consequences, especially with relationships and referential integrity concerns. Now, remember that you have that table connected to other tables. So creating a new table with a new name or different name, that will affect the relationships between this table and other tables. Therefore, using views defined as table aliases is more appropriate in these cases. Only views that define the aliases would need to be changed when the source table name is changed. We learned in a previous session how to add or drop column using the alter statement. Other column constraints also, example, we have the default or unique, may be included with the column definition. Although you added the constraints of not null for the column that will be applied to new rows, existing rows will have null values. Um, Three steps to add a not null column. Add the column as null, add data to every row, alter the column constraint to not null. And in some cases you had some errors when entering the data because you had it as not null. So you need to add the column as null first, and then you need to add the data into each row, and then change the constraint into not null. To drop non-key columns, we use the alter statement with the drop function and just drop the column. Alter table work, for example, drop column uh, date created, and that will be fine. To drop a foreign key column, the foreign key constraint must first be dropped because this one is linked to another table. So we need to drop the foreign key constraint and then drop that column. To drop the primary key, all foreign keys using the primary key must first be dropped, followed by dropping the primary key constraint, then dropping that column. To change data type or a constraint, we use the alter table, alter column. For some changes, data will be lost or the database management system may refuse the change. Since we are altering both the table and the column at the same time, then some problems might happen. To change a constraint from null to not null, all rows must have a value first. So also that's something that we need to pay attention to when we are adding or dropping a column. Converting more specific data type, example, date, money, and numeric, from our two character or variable character will usually be easy and succeed, no problems. But changing a data type from the character or variable character to a more specific type can be a problem. Example, if we alter the table artist and we alter the column birth date to numeric for 0.0, so it was for example variable character, and we want to be specific. If the information within that column does not match the numeric, then it will be rejected. If it's, for example, date and it's formatted as a date, then it will not be accepted. For adding and dropping constraints, we learned how to do that in a previous session where we used the alter statement to do that to a table. For example, alter table artist, add constraint numeric birth date, birth year check, and we check the birth date between, for example, 1900 and 2100. Which is a constraint to check on the values of the birth date to be between or in a certain range. For changing minimum cardinalities, if it was on the parent side, to change from 0 to 1, change the foreign key constraint from null to not null. Can only be done if all the rows in the table have values. Remember, you are changing from not to not null. So if anyone is empty, any row is empty, then you will have a problem. You have to fill all the information and then change it from null to not null. To change from 1 to a 0, change the foreign key constraint from not null to null on the child side. Add to change from 0 to 1, or drop to change from 1 to 0. uh, we can add or drop triggers that enforce the constraint. For changing maximum cardinalities 1 to 1 to 1 to many, if the foreign key is in the correct table, remove the unique constraint that is on the foreign key column. If the foreign key is in the wrong table, move the foreign key to the correct table and do not place a unique constraint on that table. For example, if an employee will be the parent table, employees are to have multiple parking permits. We drop the constraint that parking permit employee number be unique. So all what we do is we drop the constraint that this should be unique and you will be fine. To change the relation from one to many to many to many, then you have to build a new intersection table and move the key and foreign key values to the intersection table. This is an example of changing the relation from one to many to many to many, where a new intersection table customer artist uh, interest was created and the primary key from each table was copied as a foreign key to the intersection table. When reducing cardinalities, you have to be careful since it may result in data loss. To reduce many to many to one to many, you need to be careful, and to do that, create a foreign key in the parent table and move one value from the intersection table into that foreign key. To reduce from one to many to one, remove any duplicates in the foreign key and then set a uniqueness constraint on that key. To add new tables and relationships, add the tables and relationships using create table statements with foreign key constraints. If an existing table has a child relationship to the new table, add a foreign key constraint using the existing table. To delete relationships and tables, drop the foreign key constraints and then drop the tables. Once we understand the database from using the reverse engineering techniques and we have a data model, we can move forward and apply all the suggested changes for the existing database. This process is called forward engineering. So basically we went back, reverse engineered until we got 2.0, and then now we're going forward to implement the changes that we need. Remember to do the changes on the small test database for initial testing. Then the large test database for secondary testing before applying it to the operational database. Again, I will repeat it again and again that do not play with the operational database. That's very important. If you lost the operational database, it will be a disaster for the company. So make sure to save, backup the operational database and use test database for your changes. Some software tools can be used to create the SQL or SQL code that can be used for implementing the changes, but you have to review that code carefully before using any changes. So don't just copy paste from the internet or from a software or a dashboard software that can create automatically the code. Make sure that the code will fit your database management system. Now remember that each database management system has slight difference in the code, and that might affect the implementation for the code. So make sure that you look at the code, rewrite it, and it works in the database management system you are working with. That will be all for this session. If you have any questions or concerns, please feel free to email me, call, Skype, or come in person, and I will be more than glad to help. Thank you and have a great day.